Okay, so we're kind of going to piece this together. I'm going to take it like in little chunks and then draw a little separate diagram over here to explain what this is actually talking about. It says two chords are congruent if and only if their corresponding arcs are congruent. If I have a circle, so if AB is congruent to CD, then I also know that their arcs are congruent. So then this is going to be congruent to that. Notice you have this arrow here. That means it goes both ways. So there's a converse of it. So if I know that the arcs are congruent, then I know that the chords are congruent. Okay, moving on to the next one. Two chords are congruent if and only if they are equidistant from the center. Bring it down a little bit so I can draw a diagram. Okay, so remember distance implies perpendicular, which we'll talk about in another statement. But if this is congruent to this, so these little pieces are congruent, meaning that these are the same distance away from the center. So if AB is equal to CD, then it is equidistant. So meaning that EF and this is E, that is F, and that is G. So if FE is congruent to EG, then that means they're equidistant, which means that the chords are congruent and vice versa. And then finally, something I already talked about is that if a diameter or a radius is perpendicular to a chord, move that down here a little bit. So if a diameter or a radius, so if that is a radius and it is perpendicular to a chord, then lots of things happen. Then we know that not only is it perpendicular, but it bisects this chord and it bisects this arc. So that means that this arc is going to be congruent to that arc if it is perpendicular. So it bisects the chord and it bisects the arc. So then this goes on with the diagram that goes with your paper. Okay? So we're going to do a couple examples. Okay, so let's do example 1. I have no idea what this is going to come out to be. Hopefully it comes out right. Okay, so I know that since these chords are congruent, then these two arcs are also congruent. So if this arc is 2x plus 3, then this arc is also 2x plus 3. And I know all three of these together has to equal 360 degrees. So if I add them up, I have 4x plus 96 equals 360. Subtract 96 on both sides. And you get 264. Divide both sides by 4. And you get x to equal 66. Okay, so if you were just solving for x, or be careful because sometimes you are being asked to find the arc measure. So just make sure that you are following along with what is being asked. Let's go ahead and do Example 2. Okay, so if I know that HM equals 5, okay, so I'm going to write a little 5 in here. So if HM is 5, then I also know that MJ is 5. Let's say that I want to find out how long MP is. So MP is just this little piece right here. Also, let's say that I know that the radius is 13. So what some people like to do is they'll put a 13 in here, which is not wrong, but keep in mind this is the piece that we're trying to find. So I'm going to draw a radius from P to J. P is the center of the circle, J is a point on the circle. What we had just talked about is that we have perpendiculars. So if I take this little piece out, kind of blow it up a little bit, know it's perpendicular, that is 5. I'm looking for MP. I'm going to label that as X. Now that this radius is 13. So this goes right back to Pythagorean theorem. So 5 squared plus X squared equals 13 squared. 25 plus X squared equals 169. X squared equals, I believe it's 144. And take the square root. So X equals 12. So that means that this little piece right here is going to be 12. So then how long is MK? Well, PK is also a radius of 13, so that means MK would equal 1. Some ways of using all the properties of chords and arcs.